afternoon. Welcome to the last lab section of this semester. So if you remember, in this semester we have done a lot of experiments. In the beginning, we have performed experiments to determine the physical property of soil. For example, grain size distribution, specific gravity, liquid limit, plastic limit, plasticity index. So they are the physical properties. And then following the physical property, we have performed a lot of labs to determine the hydraulic conductivity, consolidation, and shear strength parameters. So today, what we're going to do is the last lab, which is to perform the quality control of some engineered soil. So first of all, what would be engineered soil? Basically, engineered soil may be soil that you have to improve in the field, or if you have to build an earth dam, then those material has to be engineered. Okay, so those material will have properties that should be consistent with your engineering design. Okay, so basically, the common example of engineered soil would be soil that you have applied some compaction on it. Okay, so you will have made the soil to have a specific density and then also specific moisture content. Okay, so for the quality control, the aim is, there are two steps basically. First of all, you have to bring the soil from the field or the soil that you are going to use to build the earth dam, take it to the lab, and then to determine the compaction curve, which we will discuss how you can do that in a moment. And then once you have the compaction curve from the lab, you will take the curve to your field and then perform your compaction at the field. And then what you need to do is, after some compaction process has been performed, you will need to check the properties in the field to ensure that the field properties are consistent with what you have on the compaction curve. Okay, so first of all, what I want to do is to briefly introduce to you how you can determine the compaction curve using some laboratory tests. So basically, we will follow the procedures for the standard Proctor test. So this is a mold for the compaction test. Okay, so you will need to fill the soil, put it in this mold here, and then we will use 3 layers. Okay, and then what you need to do is for each layer you will need to apply 25 flows using this this metallic rammer. Okay, and then there is a standard weight for this metallic rammer, which is roughly 5.5 pounds, and then also the dropping distance is fixed, okay, which is roughly 12 inches. Okay, so for each layer you will need to compact for 25 blows, and then you will need three layers. And then if you remember from your past experience, when you do compaction, you will have to ensure that you apply the compaction in a uniform sense. So what I mean is, suppose that this is the cross-sectional area of this mold, the soil, and then this is the soil inside, and then what you need to do is to compact the soil and ensure that everywhere will be compacted, not just one single location. Okay, so that would be the first thing that you have to make sure. The other thing is, since you are compacting the layer in 3 different layers, you have to make sure that the interface between layers are basically not causing a weak plane. So what you need to do is to roughen. Okay, you have to roughen the surface of the interface to ensure that all the layers will be interlocking well. Okay, so that would be the other reminder that you have to note. Okay, so after you have performed this compaction here, basically what you need to do is when you compact the soil, you will apply certain amount of water. Okay, in this class here, for each team, we are going to use different amounts of water. Why do we want to do that? Because we want to create different moisture contents. Okay, so 4 teams will have 4 different moisture contents. And then what you need to do is, after you have compact the soil, you will need to perform a moisture content test, okay, to determine the exact moisture content, and then also to determine the dry density, okay, dry density or dry unit weight of your compacted soil. So once you have done that, you can prepare this kind of plot, which is a plot of dry density versus moisture content. So each team here will be responsible for creating 1 data point. Okay, like what I said, each team will add different amount of soil, different amount of water. So you will have a particular set of moisture content and dry density, okay, or dry unit weight. So since we have 4 teams here, and then we want to have a lot of data for the compacted curve, basically we will combine the results from 2 other classes, okay, which is the Tuesday class and also the Thursday class. So we will have a total of 12 points. Okay, so together with 12 points, we can determine the compaction curve for the soil we have. Okay, so suppose that this is the data point that you have from the test. So what you need to do is to determine 2 things. Okay, one is the maximum dry density or maximum dry unit weight of your soil, and then also the optimum moisture content. So based on your lab data, these are the crosses are the dots. So what you need to do is, for example, you have to use a software, Excel spreadsheets or whatever, to help to come up with a fitted curve. Okay, notice that the maximum dry density should not be corresponding to the maximum density that you determine from your particular lab data. Okay, you have to do a prepare a fitted curve and then obtain the maximum dry density from your fitted curve, not from your data point. Okay, so based on the curve that you have on this graph here, this point or this value will be your gamma D maximum. Okay, and then the moisture content corresponding to the maximum dry density or maximum dry unit weight would be the OMC, which is the optimum moisture content. Okay, so that would be the compaction curve that you need to take to the field to perform a quality control test for the soil in the field. Okay, so let's talk about how you can do that. Suppose that this is a road here, okay, and then in the past, or what you have noticed is in Taiwan, okay, we have lane that is designated for the bus, okay, and then for the bus lane, basically, if you imagine the bus lane, which is supposed to have a higher capacity than regular vehicles, okay, if you only allow the bus to run on that particular lane, what we have experienced in the past is that that particular lane will experience significant damages, and then also there may be settlements, okay, because that particular lane has experienced a lot of loading because of the high capacity of the bus, okay. So in the past, okay, the Taiwan government has tried to mitigate the problem. In the beginning, what they did was to remove the asphalt or the pavement because it has been damaged. So what they do is they would simply take away the pavement, okay? Take away the damaged pavement and then put on the pavement again. However, this does not solve the problem because the real problem is the soil, the base soil that underlying the asphalt, okay, is also damaged. Okay, so what you need to do, for example, for a road usage purpose, what you need to do is you have to compact the base soil, okay, such that it has the required strength or required capacity to support the load from above, which is coming from the bus, okay, the high capacity bus. Okay, so let's say you have to compact the soil in the field. Okay, in the field, okay, we have equipment that can help you do the compaction. For example, you can have the sheep roller. Okay, you can have the sheep roller, and then there are specifications on the weight of the sheep roller, and then also the number of times the sheep roller have to go back and forth on the field to basically apply the compaction to your soil. Okay, so for example, in the specification, okay, you have to compact the soil layer by layer, just like what you have in the lab. Okay, but in the field, usually you will compact each layer, and then each layer will have 30 centimeters. Okay, so you will have a sheep roller that runs on top. Okay, sheep roller that runs on top that can help you to do the compaction. Okay, so after a certain number of times per specification, then what you need to do is, as an engineer, you have to check whether your field soil does have the desired property that you originally designed. Okay, so what you need to do is to determine the field density. Okay, so for example, this is the compacted soil that you have in the field. Okay, so what you want to do is to determine is gamma D. Okay, gamma D in the field. Okay, so what you need to do is based on the size of the material in the field, you would need to dig the hole, and then that particular hole has a particular size that you have to follow. Okay, suppose that this is the hole that you dig. Okay, so what you need to do is to find out, the gamma D for this soil. Okay, in the field you will expect that the in situ situation would be a corresponding to a moist situation. So what you really have is the moist unit weight. Okay, all right. So when you dig the hole, you will remove the soil immediately. Okay, you can basically determine the weight or the mass. Okay, the mass or the weight of the soil that you have dug out from this hole. Okay, and then at the same time you can determine the moisture content. Okay, moisture content. So you have mass, you have moisture content. How do you determine the unit weight or the density, the moist unit weight and moist density? Okay, what you need is basically the volume of this hole. How do you obtain the volume of this hole? So one suggestion may be you can fill the hole with water. Okay, you can fill the hole with water, and then since you know water has, let me write it here, basically have 1 gram per cubic centimeter. Okay, suppose that you can somehow know the amount of water that you have to add in this hole, then with the density of water you can determine the volume. However, this is not what we done in the field, because there are two main reasons. There is reason for not adding water into this hole. First, the main reason would be the water will seep through the soil. Okay, so there will be water loss. Okay, if you put in water inside. Okay, so someone may have another suggestion on how you can measure the volume, which is to basically put a waterproof cloth, in this hole here. Okay, maybe in this. I put it here. okay, with the waterproof cloth, then water cannot escape through the hole, so there will not be any seepage. However, we also encounter another problem because there may be large, sharp pebbles in the field, okay, which may penetrate through the waterproof cloth. Okay, so that doesn't work neither. Okay, so what we need to do instead is, okay, as a standard practice, what we do is to add in some standard sand. Okay. Standard sand means a sand that we know is unit weight, dry unit weight, or its dry density. Okay, so this standard sand, we know the properties in advance. So when we pour it into the field, we can, because we know the density, we know the amount of sand that we put in the hole, then we can determine the volume, which should be the volume of this hole. Okay, so if you want, okay, as an example, say, for example, okay, so suppose that the sand, okay, the standard sand, or the gamma D of standard sand is basically, for example, 1.5 gram per cubic centimeter, okay? And then suppose that the amount of sand that you put in the hole is determined to be 450 grams. Okay, so what would be the volume of sand that you have poured into the hole? Or basically, what would be the volume of the hole? 300 cubic centimeter. Okay, so with that volume of the hole, you can back calculate. Okay, you can back calculate the dry density of the basically the total moist density or moist unit weight of the soil. Okay, because again, you have the mass or the weight, and then you have the volume. Okay, you have the volume of the sand, standard sand, and then W is determined before. Okay, so with that you can determine the unit weight of soil in the field, and then what you can do is to compare it with your compaction curve. Okay, so how do you know whether your soil is okay or not? Okay, so based on your construction contract, okay, first of all, we do not expect the soil in the field to have exactly the maximum dry unit weight and optimum moisture content of your compaction curve. Okay, we basically allow the value to be percentage of these values. Okay, so if you have learned from your soil mechanics class, we have the basically the relative compaction. Okay, so in typical construction contracts, the relative compaction is roughly maybe 90% of the maximum dry unit weight of your compaction curve. Okay, so 90%, suppose that your contract specifies that you can have 90% of gamma D max. So basically what it means is if your soil in the field, okay, if its dry density and if its moisture content plots in this red region, okay, then your field soil is okay. Okay, if it plots anywhere outside this red region, then you will need to do the compaction again. Okay, so you will need to compare your field data with your compaction curve based on the amount of compaction or dry density that is allowed from your contracts. Okay, so that would be how you can check the quality of your field soil. The last point that I want to make is usually, okay, this is the optimum moisture content for your compacted soil, right? If you have moisture content that is greater than your optimum moisture content, then we will say that the soil is on the wet side of the OMC. And then if the moisture content is smaller than your OMC, we will say that the soil will be on the dry side of the OMC. Depending on whether it is on the dry side or wet side, the engineering properties of your compacted soil will be different as well. Okay, so in your soil mechanics class, your instructor may tell you how the shear strength and then also the consolidation properties may be different if the soil is on the dry or wet side of the OMC. So in a moment, your TA will demonstrate how we can, first of all, how we can perform laboratory tests to determine the compaction curve, okay, which is the first half of this lab. And then after that, we will find out basically the density, the dry density of standard sand as the second part of this today's lab.